Hi there, physics fans. We're moving on in our exploration of some of the mysteries of modern physics. We've talked about dark matter, but that's only one cosmic conundrum. There's also dark energy, a phenomena with a similar name and a totally different behavior. Dark energy will determine the fate of the entire universe, making it an ideal topic for this week's episode of Subatomic Stories. In earlier episodes, I spent a great deal of time talking about general relativity and gravity in general. That's because gravity is the force that rules the cosmos. The other known forces make stars shine, but it's gravity that tells them where to go. And gravity has been ruling the heavens since the beginning. The Big Bang caused the universe to expand rapidly, leading to galaxies moving apart from one another for nearly 14 billion years. Since familiar gravity is an attractive force during all those years, gravity has been slowing down the expansion of the universe. The question, however, is, what will win, the expansion or gravity? If you throw a ball upward, it can fall back down. It can go high enough to just get to the orbit of the Earth and start orbiting, or it can escape the Earth and fly away into deep space. The same thing is true of the universe. Big Bang theory says that when the universe began, matter was flung apart from one another with a specific speed. So, given this initial speed, the question becomes, what will happen to the mass that makes up the universe? Will the universe expand for a while and then collapse back in a big crunch? Will it expand, always slowing and finally stopping at time equals infinity? Or will the universe expand, always slowing, but never stopping? Even a basic understanding of gravity says that there are only these three options. So, in 1998, a couple of groups of astronomers decided to figure out what the truth is. What is the fate of the universe? They did so by looking at distant galaxies. They figured out how far away they are by looking for a particular type of supernova, which has a known brightness. By seeing how bright the supernova was in their telescopes, they could determine its distance. They also measured the velocity of the galaxy by looking at its color and seeing the difference between the emission lights of hydrogen in those galaxies compared to the light emitted by hydrogen in a stationary laboratory here on Earth. The light from distant galaxies is redder than we see in our terrestrial experiments, and from the amount of change of color, we can work out the speed of the galaxy. It sounds complicated, but it's the same effect as the change in pitch you hear of the engine of a race car as it drives by you, changing from coming towards you to moving away. So that's the basic experiment. Figure out the speed of distant galaxies as a function of distance. Each of the three possible scenarios have a different and distinct velocity profile, so it should be easy to figure out which scenario is true. Just how much was the universe slowing down? Was it 1, 2, or 3? You know, there's a reason we don't just do theoretical physics, and there's a reason that we do experiments. And the reason is that sometimes nature can surprise the heck out of us. Because when we asked which of the three scenarios described our universe, the answer was a jaw-dropping 4. In spite of the fact that all three scenarios predicted that the expansion of the universe was slowing, the measurement quite clearly showed that it was speeding up. Or, more accurately, the universe was slowing down for the first 9 or so billion years of its history, but about 5 billion years ago, the rate of expansion turned around and has been getting bigger and bigger that whole time. That's actually longer than the Earth has been around. It's been a long time. So, if gravity is an attractive force, it stands to reason that this observation is impossible. Accordingly, we can only conclude that gravity is a repulsive force which flies completely in the face of common sense. We know that's not true. Well, let's not get hasty. Einstein invented general relativity back in 1915, and his equations rather clearly said that gravity is really the distortion of space, and that the correct view of gravity is that matter and energy distort space and time. We talked about this over lots of earlier episodes, and it's embodied in this impressive-looking equation here. Even in the early days, Einstein was aware that general relativity clearly predicted that space was changing over time, and the theoretical prejudice of that era was that space is eternal and unchanging. So, in order to balance the tendency of gravity to pull matter together, he added a term to his equation, which included a repulsive form of gravity. This term is called the cosmological constant. The attractive and repulsive terms canceled out, predicting that the universe was stable. But, of course, in 1929, Edwin Hubble found that the universe was expanding due to the Big Bang. Basically, Einstein said, oops, or however they say that in German, and took the cosmological constant out. However, with the discovery of the accelerating expansion of the universe in 1998, general relativity needed the substance that generates a repulsive form of gravity. Astronomers call this substance dark energy, and it's an energy field that permeates the entire cosmos. Now, scientists are not entirely sure what dark energy is, but the cosmological constant is one possible explanation. The cosmological constant is a constant energy density in the universe, and yes, that means that as the volume of the universe increases, dark energy also increases. That might seem like it's a problem, but as I described in episode 20, general relativity predicts that in a changing universe, energy isn't conserved, so it's not the problem you think. There's another model of dark energy called quintessence. Quintessence is like the cosmological constant, but it changes over time. And if dark energy changes over time, it has a profound consequence on the fate of the universe. So it's important to figure this out. Currently, the data is consistent with a constant density of dark energy, but future experiments may change that. Maybe I'll deal with this in a future video. Okay, that's a lot, but dark energy is a big deal. But then again, so are questions. Let's see what questions our viewers have for us this week. Questions. There were tons of dark matter questions. Let's get started. Jonathan Hacker asks about gravitational lensing by intergalactic dark matter. Hi, Jonathan. Short answer. Yes, there is a lot of evidence. Take, for example, this picture of galaxy cluster Abell 2218, a cluster containing about 10,000 galaxies. The yellower galaxies are relatively nearby, only about 2 billion light years away. And yes, I use the word nearby, ironically. The orange and blue arcs are distorted images of even more distant galaxies. One of the galaxies is as far away as 13 billion light years. Astronomers added up the mass in the visible parts of Abell 2218, and it just isn't enough to account for the distortions. The only way to see what we see is if there's about 25 times as much dark matter as ordinary matter in the cluster. So there's your evidence. RichTalk34 asks if the final evidence for dark matter will come from an astronomical or particle physics breakthrough. Hi, RichTalk. That's easy. It'll be particle physics. There are 3 approaches to seeing dark matter: making it in accelerators, seeing dark matter interact with matter as it passes through the Earth, and seeing dark matter and antimatter, dark matter, annihilate in locations like the center of the Milky Way. The only way anyone will really believe that dark matter has been discovered is by seeing in underground detectors dark matter passing through the solar system, combined with creating it in particle accelerators. Seeing the annihilation products from elsewhere in the universe is far harder to prove. It's too easy to generate similar signals by commonplace things like pulsars and things like that. Nope, we'll see it here on Earth or we'll never believe it. Zarnia asks if the existence of galaxies without dark matter implies the existence of galaxies with only dark matter. Hi, Zarnia. The answer appears to be yes, or at least mostly so. Astronomers have reported Dragonfly 44, a candidate galaxy with the right properties. It reportedly has a mass of about the same as the Milky Way, but it emits about 1% of the light the Milky Way does. Furthermore, some astronomers claim that dwarf galaxies have a much higher fraction of dark matter than bigger galaxies. I should point out that there is a lot of controversy on this in the community. There seems some evidence for the existence of dark matter galaxies, but I might say something different next year. That's how science works on the frontier of knowledge. Welcome to my world. Rohin S. asks how dark matter formed and how did it interact with matter in the early universe. Hi, Rohin. The answer is easy. I don't know. Remember that the experimental status is that dark matter hasn't been inarguably confirmed, and we have no knowledge of the properties of dark matter particles. Until that happens, any answer to your question is nothing more than informed speculation. Max Ryan asks if a degree in theoretical physics is a good choice for a person wanting to become a theoretical physicist. Hi, Max. Well, yeah. I suppose it's possible that someone can do it on their own, but the odds of success are essentially zero. The myth of an errant genius is just that, a myth. I should warn you, however, that a degree doesn't guarantee a career. The number of theoretical physicist positions that become available at research institutions is maybe like 2 or 3 per year in the entire U.S., including all branches of physics. And theorists are all very smart, so the competition is intense. There are many more theoretical faculty positions at smaller teaching-oriented colleges, but even then, the other applicants have stellar credentials and brilliant minds. In short, a career in physics theory is a very hard path. You should have a plan B. Luckily, many industries have problems that all need well-trained and smart people. TJ Reynolds asks if the Milky Way has any dark matter. Hi, TJ. Yes. We don't have a super precise measurement, but astronomers think that the Milky Way has, ballpark, 10 to 20 times more dark matter than ordinary matter. In the vicinity of Earth, we believe that dark matter makes up about 1 proton mass per 3 cubic centimeters. That works out to being equivalent to 1 asteroid's worth of dark matter in the entire solar system. However, astronomers believe that the dark matter is not in a clump, but rather is dispersed throughout the solar system. They have underground detectors searching for the dark matter wind blowing through the Earth. So far, no luck, but we keep looking. Psychics asks if dark matter could be micro black holes. Hi, Psychics. In principle, the answer is yes, but we've looked, so the real answer is no. Searches for things like black holes have ruled out objects in the mass range of 1/3 the mass of the Moon to 100 times the mass of the Sun. Bigger and smaller are still possible. Given the amount of dark matter in the Milky Way, we can be pretty sure that it's not the form of big black holes, or we'd have seen them by now. Now, smaller black holes are not excluded, but it's hard to imagine how they could be made. Personally, I think this is an unlikely answer to the dark matter question, but it can't be ruled out with 100% certainty. Sunsparkta commented on the controversy surrounding the announcement of galaxies with no dark matter. Hi, Sunsparkta. You're right, but things are moving fast. In 2018, a group claimed to have found the dwarf galaxy NGC 105-DF2, which has no dark matter. The following year, another group said, "You're nuts. You got the distance wrong." The first group then replied, "No way, we're not nuts. We made some additional measurements that validate our first paper. Oh, and here's another galaxy just like the first one." And then another group claimed to have found 19 more small galaxies without dark matter. And so it goes. This is happening right now, and the situation is evolving rapidly. However, the scale seems to have tipped in the direction of the observation of galaxies without dark matter being true. But the pendulum may swing the other way next week. We'll just have to wait and see. Jose Paulo asks why you need electromagnetism for dark matter to clump. Hi, Jose. I guess technically you don't, but you do need a force that causes matter to stick together. Gravity can pull objects towards one another, but even if they collide, energy must be conserved, so the objects just bounce off one another. To assemble into a bigger object, they have to stick together. That means electromagnetism or something similar. Giuseppe Tumino notes that dark matter could have the same fate as the luminiferous ether. Hi, Giuseppe. Yes, it could. Okay, on a different topic, I'd like to remind you that I'll be giving an online public talk a couple of days from now via Zoom. It's called Understanding God's Thoughts, Einstein's Unfinished Dream, and it's about progress towards a theory of everything. I'll also take some questions. If you want to attend, you have to register, and I put a link in the description where you can do just that. And if you miss the lecture, we'll post it as a video on this channel a week or so later. I hope to see you there. Okay, so that's all the time we have today. I hope you enjoyed it. If you did, please like, subscribe, and share. And if you didn't, why not? How could you not? I mean, who doesn't love physics? After all, even at home, physics is everything.